PPT?
Yes, ma'am.
Yes, ma'am.
Okay, thank you. So here you can see the diagram, or you can say rather the picture of a plant of Artemisia annua, the common name for which is sweet wormwood. Okay, that is the name of Artemisia annua. And this artemisinin is a parent compound that is isolated from the leaves, dry leaves of Artemisia annua by extraction, simple extraction using solvent. Now, this particular class of artemisinin and its derivatives, it is considered to be a new class, and they are definitely structurally unique than whatever compounds we have seen up till now, be it alkaloids, 4-aminoquinolines, 8-aminoquinolines, or even quinoline methanol, like mefloquine, as well as the 9-aminoacrylene. So the structure is completely different for the artemisinin as well as its derivatives, which are used as antimalarials. Okay. Now, which are the derivatives we are going to see? We are going to see artemether, arteether, and artesunate. Now, out of this, arteether is not there in your syllabus, but then it's just a very small difference. As you can see, artemether is basically a methyl ether, while arteether is going to be a ethyl ether. So that is the only difference between these two compounds. So why not just have a look at the structure as well? So we'll just have a look at the structure of arteether as well. Now, all of these compounds, artemisinin as well as its synthetic and semi-synthetic derivatives. Now, I suppose you are aware what do you mean by synthetic and semi-synthetic derivatives. Semi-synthetic derivatives means you are taking something from natural source. Say, for example, you are taking artemisinin and then you are converting it to the its derivatives, then that would be termed as a semi-synthetic method, because initially you are taking a natural compound and then you are modifying it. You are doing the structural modification by using synthetic method. So that is why it is a semi-synthetic method. While when we talk about the synthetic method, it is going to be completely synthetic from the start itself. Okay, from the start itself, it's going to be completely synthetic. We're not going to use any natural source compound, chemical compound in this case. Is this difference clear to everyone? What do you mean by synthetic and semi-synthetic?
Yes, ma'am.
Okay. Now, all of these compounds, we will come to the details of the mechanism of action. But for now, remember that all the compounds contain an endoperoxide. So this is something which is a pharmacophoric group. I suppose you know what is pharmacophoric group. It is a group which you cannot replace. That group has to be present for the compound to show the activity. Or that particular group is going to be responsible for the given mechanism of action for the drug. So you cannot replace that group. Okay. So that group is nothing but endoperoxide in case of the artemisinin and its derivatives. Now all of these compounds, they are active against the Plasmodium genera that cause malaria. So all the 4 species which we have seen for malaria that cause malaria. So against all of them, the artemisinin and its derivatives, they are found to be active. Now, first of all, you just focus on the structure of artemisinin. Okay, then we will talk about its derivatives. So this is the structure of artemisinin. You can very well see it is containing 2 6-membered rings, right? You can very well see alicyclic rings. There is no unsaturation, there is no aromatization in any of them. So one is cyclohexane ring. The other is also a 6-membered ring, and it is containing a ester, cyclic ester. So this is called as a cyclic ester because the ester is not free. It is a part of the cyclic ring. So this type of structure, if it is present, it is called as a lactone. Okay, if it is having a cyclic ester, that means the ester is a part of the ring, cyclic ring, which is present in the structure, then that ester is called as a lactone. Okay, so this artemisinin particularly, it contains the lactone, that is the cyclic ester. And if you observe the next ring, that is the third link, you will see that it is a 7-membered ring. 1, 2, 3, 4, 5, 6, and 7. So it's a 7-membered ring, as well as it contains oxygen as heteroatom. So 7-membered ring with oxygen is called as a oxapine ring. Okay, oxapine ring. 7-membered ring with nitrogen is called as azapine ring. I suppose you must have come across some drugs which contain the azapine ring for sure. So this is a 7-membered ring with oxygen. So that is why it is called as a oxapine ring. Okay, as well as this 7-membered ring is connected to the center of these two 6-membered rings with the help of a peroxide. A peroxide means two oxygens, and there is a endoperoxide. Based on how it is formed, you can either have a exoperoxide or you can have a endoperoxide. But in this case, looking at the stereochemistry, for now you remember that it is a endoperoxide. Two oxygens are present. So this is basically a bridge. Okay, it's a bridged compound. And if you look at this ring now, particularly the one which is formed because of the bridge, so that is again a 6-membered ring, and it contains three oxygens. Okay, it contains three oxygens, one, 2, and 3. And they are in 1 to 4 relation. If you consider this as a separate ring, 6-membered ring, then this is oxygen number 1, this is oxygen number 2, this is carbon 3. So oxygen is at 4th position again. So what it is forming is a 1 to 4 trioxane ring. Why it is called trioxane? Because it is containing three oxygens. 1 position, 2 position, and 4 position. So this is how it is called as a 1 to 4 trioxane. So all of these features are present in the derivatives of artemisinin as well. The only feature which is absent is the lactone. Okay, because if you look at the other derivatives, it is not having a lactone, that is the cyclic ester. The C double bond O of artemisinin is modified in all the 3, 4 derivatives which are there for artemisinin. So is the structure of artemisinin clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay. Any doubts?
No, ma'am.
Fine. Next, talking about the synthesis, if you have to synthesize any derivatives. So the ones which are there in your syllabus, for that what you need to do is, you need to reduce this carbonyl group. Okay, that is the keto group which is present. So ketone, you know, on reduction is going to, if you treat this as a ketone, okay, ketone carbonyl group, then you can definitely reduce it to the corresponding secondary alcohol. So in the next structure, you can see the keto group is reduced and you get the secondary alcohol. Okay, so this becomes the dihydroartemisinin, because here now two hydrogens have been added. This is the one hydrogen and this is the second hydrogen. So that is why it is dihydroartemisinin. Okay, now once this dihydroartemisinin is formed, what I can do is either I can react it with methyl iodide or ethyl iodide and form the corresponding ethers, as in case of artem ether and arte ether, that is artemotil, that is also called as artemotil. So what I can do is this hydroxyl group which is formed in dihydroartemisinin, that I can react with CH3I, that is methyl iodide. Okay, so if I'm treating it with CH3I, that is methyl iodide, I will be able to convert it to the ether. And because it is a OCH3, that is, it is a methyl ether, the name of the compound becomes artem ether. Okay, while if I react the same compound dihydroartemisinin with ethyl iodide, that is C2H5I, then I will get OC2H5. Okay, so that R is OCH3 in case of artem ether, and in case of artemotil or arte ether, the R group is OCH2H5. Sorry, OCH2CH3, that is OC2H5. Is this modification clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay. In addition, the compound can also be converted to a ester. Okay. How? Because it contains the alcohol. So if you are able to add some acid to this, some carboxylic acid to this, then obviously you know it's a normal reaction between alcohol and carboxylic acid that it is going to form the corresponding ester. Okay, so that is what is happening over here. Here the added acid is succinic acid. Now I suppose you know what is succinic acid. It is a dicarboxylic acid, basically COOH, CH2, CH2, COH. So that is your succinic acid. So when you take dihydroartemisinin and treat with succinic acid, you get a hemisuccinate ester. Now what I mean by hemisuccinate ester is the one out of the two carboxylic acid groups that are present in succinic acid, it is only one carboxylic acid which is actually becoming the part of the ester. The other part is free. It is basically COH. And now it is just simply converted to the salt form. Okay, so please remember hemisuccinate means only one part of the, or you can say one carboxylic acid group of the succinic acid. It is forming the ester with the corresponding alcohol, which in this case is dihydroartemisinin ka secondary alcohol group. Okay, so that is how it is forming the hemisuccinate ester. And then once the free COH group is there, you can definitely convert it to the sodium salt by addition of sodium hydroxide. Okay, so this compound is called as a artesunate. Did you understand formation of artesunate?
Yes,
Yes,
ma'am.
ma'am.
So in this, what you're doing in case of dihydroartemisinin, you're just adding succinic acid. Okay, remember for this. Remember for now this much. Okay, and it is forming a hemisuccinate salt. Now, there is a difference in the polarity of these compounds because of the added groups. You can very well see what you have added in salt is basically polar groups, right? Carbon, oxygen, there is a polarity difference, right? Then again, you have the C double bond O. So again, you are having the polarity difference between carbon, oxygen, and here you are forming the salt as well, sodium salt. So obviously this compound is going to be water soluble, and it is actually found to be very much soluble in water. Okay. So artesunate, that is artemisinin derivative, formed by conversion to the succinic acid salt, that is artesunate. This Su comes from the succinate. Okay, Su comes from the succinate. So that is water soluble in nature. While in case of the ethers which were formed from dihydroartemisinin by reaction with ethyl iodide or ethyl iodide, whatever ethers you are forming, you are simply adding either one CH3 group or two CH3 groups. So in this case, you are adding a non-polar moiety, because of which both of these ethers, artane ether as well as arte ether, which is also called as artemethyl, they are oil soluble. Okay, they are no more soluble in water. They are soluble in oil. Okay, so that is the main, what you can say, things which you have to know and you have to remember from the exam point of view. They would ask you give example of a water soluble artemisinin derivative. The answer is artesunate. If they ask you give example of a oil soluble artemisinin derivative, your answer should be artemethyl. Okay, while artemisinin or its derivative which contain lactone. So in that case, the only example would be artemisinin, because in others the lactone has been converted, or rather the lactone's carbonyl group is reduced to the hydroxy group in dihydroartemisinin, to the ether in case of artane ether and arte ether, as well as to the hemisuccinate salt in case of the artesunate compound. Okay. Okay, is this much clear to everyone? Then only I'll go to the next part. Any doubts?
No doubts, ma'am.
Okay. So, what is observed is whenever such compound you are using, that is dihydroartemisinin, it is observed that when you are preparing the oil soluble ethers, that is either the methyl ether or ethyl ether, it is seen that the beta isomer predominates. What I mean is this hydroxyl group in dihydroartemisinin It could be either in the alpha form. Alpha means you will show it with the dotted line, right? This way. So either it would be in the alpha form or it would be in the beta form. Beta form you show with the solid bonds, right? So what is observed is whatever ethers you are making, the oil soluble ones, they have the beta form. That is, dihydroartemisinin in beta form will react to form the ethers, methyl ether or the ethyl ether. While for the preparation of the water soluble salt, that is the RTS unit, you need to have the alpha form of the hydroxyl group. So you can very well see here the RTS unit is the alpha form, while Artem ether and Arthe ether, it is the beta form. Okay, I suppose you know alpha means it is going inside and beta means it is coming outside. Okay, so it is basically the configuration around this carbon to which the hydroxy group is attached. Is this clear to everyone? So, though this is a single slide, but there are various concepts which you should know. One more thing which I missed out is this artemisinin and its derivatives. They are termed as sesquiterpenes. Now, what I mean by sesquiterpenes is basically terpene means a compound which contains a isoprene unit. So, in case of sesquiterpene, it is the three isoprene units which actually go on repeating. I suppose you have seen the structure of terpene in cognosy somewhere, right? So in that, if you are just having three isoprene units, then it is considered as a sesquiterpene. So that is the meaning of sesquiterpene. So some terminologies you need to remember. This slide I have added after I have shared the PPT with you. So I will share the PPT once again today. Okay. So sesquiterpene means a compound which contains three isoprene units. Lactone, we have already seen the meaning. It's a cyclic ester which is present in the artemisinin. Hemisuccinate means only one acid group is esterified, one acid group of successor